Well, that's all I wanted to say about Lewis's analysis. I've covered how Lewis defines time travel, his way of diffusing grandfather paradoxes, his account of change in the past, and his account of causal loops. What I want to do for this final section is simply to sketch some of the live problems in the philosophy of time travel and where this branch of philosophy is going next. One of the interesting questions concerns persistence in time travel. Suppose you travel back in time and you meet your younger self. You have a conversation with your younger self, something along the lines of the phone call that Lewis imagines. How can one person be present in two places at once? How did time travel suddenly allow you to bilocate? Interesting questions from physics and time travel concern what sort of laws of nature would govern a physical world that had systems that time travel in it. A fascinating argument from David Deutsch and Michael Lockwood argues that a realistic physics of time travel would have to imagine that time travel takes place in many, many histories. Suppose, on this view, you travel back in time and you try to assassinate Hitler in 1908. In a one-world system, and Lewis's analysis is part of a one-world system, there seem to be certain physically possible outcomes that you can't achieve. You can't shoot somebody dead for all that the person is unarmed and unarmoured. So, Deutsch and Lockwood argue, backward time travellers would face very strange physical blocks. There would be apparently physically possible actions that you couldn't perform in the past. And they think that it's a constitutive part of a realistic physics that local systems, local agents should be autonomous, in the sense that what is possible in a given region of space-time should be determined by what's going on in that region and not reflect facts about all of space-time. So, Deutsch and Lockwood think the way to make time travel consistent and also preserve a realistic sense of physical possibility is to imagine that time travel takes place in a system of many worlds or branching histories. So you travel back in time to 1908 and you can assassinate Hitler, but the Hitler you assassinate belongs to a history that branches off from the history whence you come. So yes, you can have your full freedom of action, your full autonomy in the past, but if you change history in the replacement sense, the history you arrive in is distinct from the history you left. So, to go back to the Hitler example, you could assassinate a version of Hitler in 1908 and create an alternative history, a history that branches off from the history that you come from. But there's no paradox here because there are now two versions of Hitler. There's the Hitler from your history who dies in 1945, and there's the Hitler in the history that you create who dies in 1908. So you could have your full freedom of action without generating paradoxes at the cost of accepting the existence of many worlds. And an interesting question is, does many worlds time travel really qualify as time travel? If your destination is in a different history, a different chain of events, is that really travelling in time? Another problem concerns whether or not a realistic physics would let us construct time machines. Now this is a region where we're looking at the intersection of quantum mechanics and the general theory of relativity, and a lot of work remains to be done to make those two very different and very successful theories into a single cohesive theory of quantum gravity, as it's called. And an interesting question is whether the mechanisms for time travel that general relativity may permit and the time travel mechanisms that quantum mechanics may permit will survive the fusion of general relativity and quantum mechanics into quantum gravity. At the moment, one interesting line of approach, particularly associated with the philosopher John Ehrman, holds that it might be possible to construct a realistic time machine, but at the cost that you couldn't control it. You could set up the conditions necessary to generate divergences between personal time and external time, but it would be physically impossible to predict what that mechanism would actually create. So you could set up a time machine, you could create a region of the universe where time travel occurred, and yet not be able to predict what sort of outcomes were generated by it. I mentioned Stephen Hawking on Big Bang cosmology earlier, and Hawking has posed a great challenge to the realistic possibility of time travel, which is often quoted, which is, if time travel is possible, where are the time travellers? Now, I stress that Lewis's analysis is concerned only to support the logical possibility of backward time travel. Something can be logically possible, but yet physically impossible. So Lewis did accept that a world in which backward time travel occurred might have some very, very strange coincidences in it, some very strange failures of causation, and might look very unlike the world that we think we inhabit. And some philosophers have tried to argue that if backward time travellers did exist, we would be able to spot them because of the unlikely chains of coincidences that they would trail in their wake. Suppose I go back in time to Vienna in 1908 with a bus full of assassins, and we each take a separate mechanism for trying to whack Hitler. Somebody has a machine gun, someone has a bazooka, someone else has a poisoned hat, someone else has an exploding cake, and we all converge on Hitler's known history with our various infernal devices. No matter how many times we try, we're guaranteed to fail. And surely this argument runs, this is associated with the philosopher Paul Horwich in particular, surely Horwich's argument runs, if backward time travel occurred, we would see trails of unlikely coincidences as people try to change history and fail. Now there may be an answer to Hawking's "where are the time travellers?" depending on the kind of mechanism that you imagine time travel involving. I mentioned Kurt Gödel's model of general relativity, according to which an infinite amount of matter distributed across an infinite space-time creates a universe where any 2 points in history can be joined together, where you can travel anywhere in space and time. Now, if we lived in a Gödel universe, the absence of other time travellers would be a real problem, because in a Gödel universe, the whole of history is accessible. But other scenarios are more localised. When physicists talk about time travel, they talk about the possibility of closed time-like curves. A closed time-like curve is a path through space and time that returns to the very point whence it departed, but that nowhere exceeds the local speed of light. It's a pathway that a physically possible object can take that leads backward in time. And it's still a hotly disputed question whether a realistic physics allows closed time-like curves. But one thing that physicists are agreed on is that a device that generates a closed time-like curve is not a vehicle. It's not like the time machines that we see in fiction, the wonderful assembly of brass and quartz rods that lets you rove through history at will. Rather, a time machine, as physicists describe it, is a kind of place, a region of curved space-time. So suppose I create a closed time-like curve generator in 2015. Thereafter, it should be possible to travel back to 2015, but the closed time-like curve generator only allows access to history over the period over which it itself exists. So if the first ever closed time-like curve generator comes online in 2015, that means that subsequent times can travel back to 2015, but nobody can travel further back than 2015. So the answer to Hawking's question, if time travel is possible, where are the time travellers, may well be that time travel is possible, but not yet. For more information about Gödel, about Lewis, about Deutsch, about Horwich, for some references and for some diagrams, please see the handout that goes with this talk. Thank you very much.